Welcome, everyone. In today's lesson, we are going to talk about two of the most important results in all of probability theory. That is the Markov's inequality and Chebyshev's inequality. We are going to cover the statement of each inequality, prove each one rigorously, and then work through concrete examples so that we can see exactly how we use it in practice. So grab your pen and let's get into it. Before we start, why do we even need Markov inequality? Why do we need it? Why do we need Markov's inequality? So imagine you know that the average income in a city is, let's say, $50,000 per year, and someone asks you, what is the probability that a randomly selected person earns more than 200,000 per year? One, you do not know the full income distribution. You only know the mean. Can you still say something useful about that probability? The answer is yes. And Markov's inequality tells you exactly how. So it gives you an upper bound on the probability that a non-negative random variable takes a value that is very large using only the mean. So first, let's state it clearly. Let x be a non-negative random variable. With an expectation, okay? X. And let A be strictly positive. Then the Markov inequality states that probability of x greater or equal to A is less or equal to the expectation of x all over A. So this is the Markov inequality. In words, it states that the probability that x is at least A is at most the mean of x divided by A. Now let's pay attention to two things. First, the x must be a non-negative random variable, and A must be strictly positive. Okay, so we need to pay attention to this statement. Now, let's prove this inequality. We are using the continuous case. We can do the same thing for the discrete case. But for now, let's look at it for the continuous case. So we have that let's first start step one. We want to write the expectation as an integral, right? We can all do that. So we have expectation of x is given as integral from 0 to infinity x f of x dx. So we can all write the expectation as an integral. Now the next step is to split the integral at a. So we have expectation. So for step 2, we have expectation of x to be equal to, we want to split the integral. So a to 0 x f of x dx plus integral sorry 0 to here 0 to a 0 to a. Then the next one will be a to infinity. So a to infinity x f of x dx. We have split the integral into two. Let's look at the third step. So third step will be to drop the first integral. Okay, so we know that x is greater than or equal to 0. So this will give that x f of x will also be greater or equal to 0 for all x. So the first integral is non-negative. We know this integral from a to 0 x f of x dx is non-negative. So it's greater or equal to 0. Non-negative, okay? We know this. Then, if that is the case, then dropping this that we know is non-negative, we will have expectation of x to be greater or equal to a to infinity x f of x dx. Because we have already stated that because x is non-negative, this integral will also be non-negative for all x. In that case, if expectation can be split into these two, and we know this is non-negative, then the expectation of x will be greater or equal to just this one. Look at it this way. You are saying that, let's use numbers. Say 5 is equal to 3 plus 2, right? Let's take this. 5 here is the expectation of x. I'm using it as an example, which is equal to something here plus something here, which are all non-negative. They are all positive, okay? So if we are saying that we want to remove this guy out of the equation, then 5 will obviously be greater or equal to 2, because if they are all positive, look at it that way. So expectation of x is greater or equal to the other expectation. Now let's bound x from below. On the integral, we have is a to infinity on the integral, okay? That's the interval. We know that x is greater or equal to a. So then we can replace x with a smaller quantity of a. If we do that, we will have a to infinity x f of x. If we replace the x with a smaller quantity, so say replace x with something smaller. So smaller quantity, then this expression will be greater or equal to, say, a to infinity. Now the x is replaced with a, which gives us a f of x. And we all know, since a is a constant, we can bring it out of the integral. I forgot to bring the dx. So a can be out of the integral. But recognize something. That's step 6. if we have expectation of f of x dx, this is the same as probability of s greater than or equal to a. So this is from a to infinity. If we have this expression from recognition, step 6, the integral of f of x dx will be equal to the probability of x greater than a. So let's put everything together in step 7. So we will have expectation, step 7, expectation of x greater or equal to integral a to infinity x f of x dx, which is also greater or equal to a times the probability of x greater than or equal to a. That's if we tie everything together. So let's simplify it. We will end up with, since a is really positive, we will have probability of x greater than or equal to a being less than or equal to expectation of x over a. Acts are required, and this completes the proof. The key insight is simple. We drop part of the, what you need to do is define the expectation. In the case of continuous distribution, you define the expectation, then split the integral into 2, then you drop part of the expectation and replace x with a smaller value, which is a, giving us a lower bound on the expectation of x that involves exactly the probability we wanted. So that completes the proof. Now let's look at an example. Suppose we have the average income in a city to be $50,000. What is the upper bound on the probability that a randomly selected person earns more than 200,000? So from the question, we have expectation of x to be equal to 50,000. And this is income, so we know it will be non-negative. Then our A given in the question is 200,000. First, A is positive, strictly non-negative, which is positive. And the expectation of X is given as 50,000. We are dealing with income here, which we know will be a non-negative random variable. So the probability of X that's being asked, probability of X greater or equal to 200,000 will be less or equal to the expectation of X over A, which is giving us 50,000 over 200,000, which is equal to 1/4, which is 0.25. So, applying the Markov inequality, we can say that no more than 25% of the people can earn above 200,000. regardless of how income is distributed, as long as it's non-negative. So we notice how powerful this is, where we use only the mean and got a meaningful bound on the tail probability. This will be the end for the Markov inequality. The next lesson will be on Chebyshev's inequality.